So what we're looking at in this unit is overall energy changes in reactions, whether that be a chemical reaction or something like the solution process. But it's basically the energy lost or gained in that process. So previously we've learned about Q equals mc delta T, and being able to calculate the energy change when a piece of metal is transferred to water. We've talked about the energy changes during phase changes, that you've got to use the heat of fusion or the heat of vaporization. And now what we want to look at is the amount of energy that changes when a reaction proceeds. So we're all pretty familiar with reactions that produce energy. You think about burning something, and that produces heat and light, and that's an exothermic reaction. But the question is, how much does it make, and how much per mole or how much per gram does it make? And we want to look at those types of things in this unit. We also want to look at reactions that gain energy. You might not think too much about that, but there are reactions that gain energy and they feel cold. So think about that instant cold pack that you might use, where you smash the bag and it produces a chemical reaction where the solid comes in contact with liquid and it gets cold. Right? That's an endothermic reaction. It's absorbing energy. And so we can use these energy diagrams as a way to represent this. And these are some of the first questions that you're going to examine in this unit. If we look at our first example over here, we got the reaction of N2 plus O2. These are our reactants. And our products are up here. And so overall, as we go through the course of this reaction, the reaction is going to gain energy because our products are at a higher energy than our reactants. So how much energy are they going to absorb? Well, the difference between the end and the beginning. And so you see that here on the scale, the energy absorbed is that height there. Now, what is this little mound right here? Well, all reactions have what we call an activation energy, where they need a certain amount of energy in order to get going, right? It's kind of like that rock at the top of the hill that you got to give it a little push before it starts rolling down that hill. So both endothermic and exothermic reactions have an activation energy. And so the activation energy is the energy required to get that reaction going. And so in this case, this endothermic reaction does have a higher activation energy. It's going to require the absorption of this higher amount of energy in order for the reaction to proceed. Even in an exothermic reaction, if we look at the other example here, this is an exothermic reaction. Its reactants are at this energy, its products are at a lower energy, so net it's releasing energy. But in order to get going, it's got to get up and over that energy barrier. It's got to absorb this activation energy before it can release the amount of energy that's going to be released. So these are visual energy diagrams that show us what's happening in an endothermic or an exothermic reaction. The difference in height is the energy that's either absorbed or the energy that's released. We're going to represent that energy as delta H, and we call that the enthalpy. So the enthalpy of a reaction is the energy that's absorbed or the energy that's released, right? They're both going to be the enthalpy of that reaction. An endothermic reaction is going to have a positive enthalpy change. An exothermic reaction is going to have a negative enthalpy change. Basically, think about it this way. It's the difference between the energy content of the reactants and the energy content of the products. So in an exothermic reaction, that energy content has to go up, whereas in an endothermic reaction, that energy content has to go down. So here I summarize it a little bit. It says energy absorbed or lost in a reaction is called enthalpy change, and we can think of enthalpy as that heat energy. The enthalpy of a reaction is expressed as delta H and has the unit kilojoules per mole. And so here's an example of a combustion reaction. CH4 is methane. So the burning of methane, reacting it with oxygen, is going to produce carbon dioxide, water, and heat. So the question is, how much heat is lost or gained in a reaction? In this case, it's going to be heat that's lost. but in some reactions, it's going to be heat that must be gained. And in this unit, we're going to explore 3 different ways that we can calculate the overall heat of reaction, right? The overall heat of reaction is that delta H, that enthalpy change. And so the 3 different methods that we're going to use, that we're going to look at, one is using heats of formation, and that's from a reference table. The other is we're going to use Hess's law, and that's where we're going to take some reactions where we do know their enthalpy change, and we're going to combine them together and combine like terms and cancel terms that are on both sides, and we're going to use that process to figure out the enthalpy change for our reaction. Or we can use the calorimetry process, and you're going to see in this unit we will do a lab and we dissolve some substances in water, and so that solution process is either going to absorb heat or release heat. And so by measuring what's happening to the water and the heat that the water is gaining or losing, now we can know what's happening to that solution, that solute, whether it's releasing or gaining heat itself. So 3 different methods that we can use to determine the delta H, the enthalpy change for a reaction. We're going to examine all 3 of those in this unit.